Okay, YouTube, in our last video we looked at matrix multiplication, kind of the processes behind that, but specifically with multiplying two 2x2 matrices. And what we want to do kind of in this video is extend this to be true for any, I guess, ordered matrices so long as it is defined. And so we're going to talk about the definition of matrix multiplication in general here. And we would say that in general, the process of example number 5, and this was this matrix multiplication problem we did here in this last video. Let me see if I can pop back over there. We can take a look at it. Again, we looked at this row by column multiplication here between a couple of 2x2 matrices. But looking at this, we had a 2x2 matrix times a 2x2 matrix, and we were continuously taking the row elements of the first matrix times the column elements of the second matrix. So with regards to what this means in terms of their orders here, we would say that to multiply an m by n matrix and an n by p matrix, the two inner dimensions here essentially are going to need to match. So when we kind of illustrate this, and this is what I want to do here, let's say we have a couple of matrices, and we're going to call this one A, we'll call this one B just because, and let's say this, we have an m by n matrix, and this one here is an n by p. Well, kind of exploring what this would mean, it would mean that the number of columns, okay, the columns on the first matrix would be equal to the number of rows on the second matrix. And so we're going to make a little note here. These are equal. If these are equal, then we would say that matrix multiplication is actually defined. So we say that for the product of two matrices to be defined, the number of columns of the first matrix must equal the number of rows of the second matrix. But essentially what this would imply is, let's say, in our last example we had a 2x2 times a 2x2, we could see that having two columns in the first matrix and two rows in the second matrix, what that does is it guarantees that you have just as many things in this row that you have in this column you're about to multiply. And so looking at it this way, we're just kind of trying to ensure that everything in this row is going to have something to multiply by everything in this column over here. But the way we generalize this is we say that the number of columns in the first matrix has to be equal to the number of rows in the second matrix. So to write this stipulation a little bit more succinctly, we could say that matrix multiplication is defined. Let's write a little note here. Matrix multiplication is defined if and only if the quote-unquote inner dimensions match. So what I mean by inner dimensions here is that if you actually write these two matrices side by side, like m by n times n by p, you can see that these two inner dimensions actually are going to match with one another here. So that being said, let's go ahead and read this general definition of matrix multiplication, and then we'll extend it in a couple of examples here. So we say that the product of an m by n matrix A, so we have a matrix A, and A is m by n. So we're going to write a little note here. A is some m by n matrix, and an n by p matrix B, so the product of these two things, and B is an n by p matrix, okay, is an m by p matrix. So we're going to make a little note here. This m by p matrix, where are they getting the m in the m, or the m in the p, excuse me. One thing we want to write here is that we have the inner dimensions match, okay, match. We know that that has to be the case in order for this to be defined. But one thing I want you to notice is that the outer dimensions, m by p, these will be the dimensions, okay, of our product. So this is a pretty neat thing. Basically says that you can multiply two matrices as long as the inner dimensions match, and the size of our answer here, and I'm going to call this our product matrix P, is some m by p. So these are the dimensions, okay, of our product, and these are, I guess we'll say, the outer dimensions. Outer dimensions are our product dimensions. That's how we'll state it here. So that's always basically going to tell us the size of our answer here. So again, we say that the product of an m by p matrix A and an n by p matrix B, where the inner dimensions match, is some m by p matrix AB. We're calling it the P here for the product matrix, but we say whose elements are found as follows. And so in general, it says that the element in the ith row and the jth column of AB. So in other words, the elements in this matrix over here, where we're saying that these are little p and they're in the ith row and the jth column, okay? We find this by multiplying each element in the ith row of A by the corresponding element in the jth row of B and adding the product. So essentially, kind of like we saw in the last video, we would say that if we want to find the pth element, or the little p, in the ith row in the jth column, then what we'll do is we'll take everything in the ith row of the first matrix times everything in the jth column of the second matrix, and we do it component-wise. So you can see color coding this. We would take green times green plus blue times blue plus purple times purple, and all of that multiply out, add together, it ends up being the entry that is in that row column pair that we multiplied there. So, excuse me, that being said, let's go ahead and take a look at what I mean here by doing this. We're going to be given a couple of matrices here, A and B, and you can notice that they're not the same dimensions here. As a matter of fact, underneath A, let's go ahead and write the dimensions. We say how many rows, how many columns. We notice that it has 1 row and 3 columns. Excuse me. And that B has 3 rows and 1 column. So when we're finding the product of AB, okay, again, AB, my recommendation is to actually write these out in roster notation, or just kind of write them out explicitly. So A is this 1 by 3 matrix 1, 2, 3, and we're taking it times B. Now it's going to seem weird to stack these next to each other. You can kind of stack them however you want. We're just multiplying them. But this is 4, 5, and 6. So as we multiply this, looking at our dimensions, and I would recommend you write your dimensions down here, 1 by 3 times a 3 by 1. The first thing we want to assess is this defined? And because our inner dimensions match, we have a match, okay, then that means that we're actually going to get an answer here. So the first thing we do is we write our blank product matrix first. And that product matrix, the interesting story here is, has to have the dimensions that we see on the outer 2 dimensions here. So the cool story here is we actually get a 1 by 1 matrix. Now, you're like, why are you writing this so widely if this is a square matrix where the rows equal the columns? Well, because what I know is this. We are going to, in order to find this first row, first column entry here, going to have to take every number in the first row of our first matrix times every number in the first column of our second matrix. So we're going to start with 1 times 4 here. We say 1 times 4 is 4, plus now 2 times 5, which is 10, plus now 3 times 6, which is 18. What we end up with is this 1 by 1 matrix here, and I'll write this a little more square this time. 14 plus 18, I believe, is 32. So we get a 32 here is our product matrix. Now the funny story is if we look at this product B times A, which, by the way, writing this out, we would just go ahead and switch the order of our 2 matrices around here. So our 4, 5, and 6, this 3 by 1 matrix, okay, would have been first in the product, and our 1 by 3 matrix would have been second, where we have 1, 2, and 3 as its entries or elements. So looking at this here, we would say, well, first of all, is this defined? Well, yes, this is definitely defined, you guys, because the inner dimensions match. We have a match. So what this means is our product, okay, is going to have these outer 2 dimensions in that order. So what I'm going to get here is a 3 by 3 matrix. So I'm going to make room here, as a matter of fact. I'm going to write 3 rows, each having 3 entries in it, so 3 columns as well. And in this case, what we're going to have to do is 1 by 1 go through here and say, well, what do we want to find? Now, here we're finding first row, first column. So what we do is we take everything in the first row of our first matrix times everything in our first column of our second matrix, and you'll notice that there's not much to multiply. As a matter of fact, we take 4 times 1 and we're done. So we get 4 times 1 comes out to be this entry here. Now, looking at this next entry, first row, second column, we'll go first row, second column, we say 4 times 2 there. 4 times 2 would give us 8. Now our first row, third column, we'll go first row, third column, we get 4 times 3, so we get 12. So now moving down, we'd say everything here is going to be in the second row. We'll kind of pick it up here a little bit. 2, 2, and then 2, column 3. So we would say second row, everything here is going to be second row. We'll go second row times the first column, second row times the second column, second row times the third column. In this case, we get 5 times 1 would be this here. 5 times 2 would be this here, and 5 times 3 would be this here. And then our last row, which is our third row, first column, third row, second column, third row, third column, we would go third row times first column, which is 6, third row times second column, which is 12, and then third row times third column, 6 times 3 is 18. So this would be our product here. So the interesting thing is we could witness here that the products, you know what, let me try to make some room here. Let's see if I have somewhere to write. I suppose we could say that the products the product of AB and BA were not equal. So that is to say that matrix multiplication, okay, is not a commutative operation. And so that matters with order. So we say order matters when we multiply matrices. And that has to do with our dimensions matching, inner and outer dimensions being the dimensions of our product here. So what I want to do is really quickly here, take a look at just one more example here where we want to find, say, these two products here, and we'll multiply these in different orders. So we'll start with this first product here. We have some matrix, I don't know what it's called, so we'll just say some 2 by 2 matrix here, times some, looks like 2 rows and 4 columns. So looking at a 2 by 2 times a 2 by 4, looks like our inner dimensions do actually match here. And so what we're going to get here is a 2 by 4. So I'm going to go ahead and write my blank 2 by 4 matrix here. So 2 by 4, first we would say has 2 rows and 4 columns. So we would just go ahead and fill in kind of these blank entries here. And what we're going to do is we're going to go through one by one and kind of figure these out. So first row, first column, first row, second column, first row, third column, first row, fourth column. So we'll start with all of our first row entries here. We'll just go a column at a time. So we would get first row times first column. We get 1 times 2. So we get 2 plus now 3 times 0. We'll move over, we'll move down. 3 times 0. So we get 0. Now we'll go first row, second column. So we get 1 times 3, 3, plus now 3 times 5, 15. So going across, now we'll go first row, third column entries. Beginning of the first row is 1 times beginning of first column is -1. 1 times -1 is -1. And then we move over and down. So we say 1 times -1, 3 times 4, 12. And then now our first row, fourth column, we'll go 1 times 6, 6, plus now over, down, we go 3 times 1 is 3. And so I'm going to clean this up at least a little bit here. Looks like we get 2 plus 0 is 2, okay? 3 plus 15 is 18. We get a -1 plus a 12 is an 11, and then 6 plus 3 is a 9. So now moving on to our second row, let me change my color over here. Perhaps if we go with like a green, that'd be pretty contrasting here. We'll go second row, okay? All of these are in our second row, 2, 1, 2, 2, 2, 3, 2, 4. But we'd say second row, first column, we'll go 0 times 2, 0, plus 2 times 0, which is 0. So we get 0. Here we would now go second row, second column. So 0 times 3, 0, plus 2 times 5, 10. So we would get 10. Now second row, third column. So we go second row, 0 times -1, 0, plus, now move over, move down. 2 times 4 is 8. So we get 8. And then last but not least, second row, fourth column, 0 times 6 plus 2 times 1. So 0 times 6 is 0 plus 2 times 1 is 2. We would end up with 2. So here's our 2 by 4 product matrix here of the original 2 matrices. Now when you look at, I guess, example B, I don't know if you've quite seen this yet or noticed it, but I guess my intent here was to include this screenshot. It's a good screenshot because you look at this and you say that the inner dimensions don't match. And so we would say that multiplication is undefined. And when we give a rationale or reason why multiplication is undefined here, we're going to say that we have an inner dimension mismatch. And when you try to do this on a graphing calculator, as a matter of fact, you will see that it'll say error dimension mismatch, and that just means you can't do it. So really quickly here, let's take a look at some properties of matrix multiplication just to be clear about some things. But we would say that on number 1, our associative property just kind of shows us here that we could do A times B first and then take that times C as long as the dimensions all work out there. Or we could take B times C first and then do A as long as A has to be on the left. So as long as the order goes A, B, C, A, B, C, then that would work for us here. Now our distributive property, this is kind of interesting also. It says that you could actually add matrix B plus matrix C first in parentheses and then take what you get there on the left times matrix A. Or this would be the same thing as if we said A times B in that order plus A times C in that order and then added those together, you get the same thing. So likewise, we could left-hand distribute, but you notice, and this is important here, when we right-hand distribute, we get A times C purposefully plus B times C because C is on the right-hand side. Last but not least, our associative property of scalar multiplication. Remember that C is just some real number, then we could just kind of distribute that through a matrix there, component-wise. So with the scalar C, we could take C times some product AB. So this says we do the product of the two matrices first and then scalar multiply. But that would be the same thing as if you just threw the scalar into A and then did that new matrix A times the matrix B, doing matrix multiplication, you do the same thing. So that's how we kind of work matrix multiplication in general, and those are the properties of matrix multiplication. Cheers.